Hey everybody, welcome back to Young Engineers of Today. I hope you had a good holiday. I didn't realize actually we were going to have Monday off until uh, Monday, but uh, you know I'm sure you guys realized it in time too, and you got to enjoy some extra free time after school. Anyway, we finished up with uh, 3D printing and SketchUp last Wednesday. Today I'm going to spend a little bit of time talking about CNC machines and how they generally work and stuff like that. And I know it says Fusion 360 here. We're not actually going to use Fusion 360. The program itself is a little bit esoteric, arcane, strange, finicky. Really, pick the best word for you. Anyway, but that's what we're going to talk about today. And then next week, we're going to move on to a new topic entirely. So this is just kind of a one-off session. It might be a little bit shorter than normal. Might not be. We'll see. Depends on discussion and things like that. But basically, we'll do as much as we can. Did you guys actually have Monday off from school as well? Nice. Excellent. No. We got one yes and one no. Well, apologies if you did not. Awesome if you did. Oh, and Tuesday. Wow. Look at that. That must have been pretty awesome. Well, there you go. Yeah, it was a pleasant surprise. Oh, I'm sorry, Jean-Marc. Oh, it didn't, Liam? I'm sorry to hear about that. Are you missing something, or? Oh, yeah, that's bad. Oh, that's no fun, Noah. Well, at least you got school off, although generally being very sick doesn't mean that you can enjoy it very much. Well, okay, so, you know, I guess back to the topic at hand. Hopefully you get the new motherboard soon, Liam. Um, Basically today, like I said, is going to be about CNC machines and how they work in a very broad sense. This is not going to be terribly in depth. Again, this was something that was more an introduction to using Fusion 360, and as you can see, there was a fairly long presentation and a lot of slides that went into making this. Yeah. So there was a fair amount of work. It was all involved. It all involved building a bookshelf. But we're not going to get into that. Um, if you guys continue with Young Engineers and you start taking the high school classes, you probably will spend some time working with Fusion 360, just because that's one that we tend to use each year, at least in the spring. So there is that. If not, though, you might get some exposure to it later on. Certainly, if you get a job in mechanical engineering or civil or even some forms of electrical, uh, you'll get lots of experience with CAD software, just computer-aided design, and utilizing that stuff. So, whatever. Anyway, CNC machines and how they work. So CNC stands for Computer Numerical Control. Uh, the thing about a CNC machine is it can be a mill, it can be a lathe, it can be a cutter, it can be, um, you know, whatever. The important thing is that the process and the machine itself is controlled by a computer as opposed to humans. In the past when you're using like a mill or a lathe or whatever, you would physically move the material with your own hands in order to make the cuts that you needed, and you'd do very, very precise machining, and a lot of times they had a whole bunch of different wheels and knobs on them, so you could move the material around at different rates to do more or less precise cuts, to move the material faster or slower. If you've ever seen like an old school lathe, you flip the thing on and you've got basically, hold on, let me find a picture. So you put material right here, turn on the lathe, it starts to spin, move it towards the cutter here, and you can adjust the rate at which you move it towards. You can adjust the height of the material versus the cutter, and in doing so, you can create some very precise parts and things like that, generally from cylindrical materials, because naturally those work the best with a machine that spins it along its axis, or its vertical axis. So that was sort of how it was done in the old days, and it required a lot of practice and experience and precision in order to make something like that. Now we've simplified the process by just making a computer do it, and the computer can do it with very, very good accuracy. In fact, because it's a computer. Same thing with cutters and stuff like that. There's something to be said for the human aspect of it, but the things like computer-controlled cutters and stuff like that, they take the human error out of it. For the most part, obviously there are still some things that humans can do to screw up the process, but that is their main advantage. And on top of that, CNC machines are generally subtractive processes. So the lathe, you'll remember when I was describing how it works, you stick some material into the chuck, and you spin the material and you cut stuff off of it. You basically shear material off in order to generate whatever you need, whether it's some sort of a specialized rod or a joint or whatever. The point is, you start out with more material than you end up with. And that's what makes a subtractive process. So when we talked about 3D printers last time, they were additive processes. Well, 3D printing is an additive process in which you end up with more material than you started with, at least in a given area. Now, you could start arguing semantics and say that, like, there's no material actually added when you're using something like a 3D printer, because all you're doing is you're reshaping the plastic that's already spooled and like fed into the print head on the 3D printer and all that stuff. And you would be right, but we're referring to specifically the object itself. In a subtractive process, the object you want is generally sort of hidden inside of a larger bit of material, and you cut away material in order to reveal it, if you want to think about it like an artist. There's this phrase, the sculptor, there's already art that sits inside the marble, and a sculptor's job is to bring it out. So sculpting is a subtractive process if you're talking about marble work with chiseling and stuff like that. Whereas, working with like Play-Doh would be an additive process, because you would pull Play-Doh out of the tub, and you would shape it, and you might add more Play-Doh to it, and add like if you're making a dude or whatever, you'd add like little Play-Doh arms and things like that. Um, and that's how it differs from, you know, a subtractive process. Even though you're not actually, like, you're not creating material out of thin air in order to add it to this. The object that you want essentially doesn't exist until you start reforming other material in order to create it. Apologies for my dishwasher. So because CNC machines rely entirely on computer control, there is actually very little in the way of human input during the actual milling and cutting process. Basically, we as people, when we're working with a CNC machine, the most we can do is you know, level the table that it works on. We can stop and start the process, reset it, set it back to zero, run diagnostics programs, things like that. But there's very little you can do to actually affect the process of milling or cutting something. Really, that's just leveling the table and starting and stopping it. That's like that. That's pretty much the extent of human interaction with most CNC machines. And that again is to keep or calibrating the machine, starting and stopping the process, I guess is a better way to put it. That is to keep the, you know, the process as rigidly controlled as possible, because computers, well, again, their main disadvantage with respect to humans is they can't account for outside situations unless they're specifically told to, and unless they're specifically given a way to like recognize that the situation is different. So, you know, if you as a person are working with the CNC machine and it starts doing something, and then you just, you know, you pull the board that it's working on like 3 inches to the right, which, by the way, never ever do that. I really don't recommend doing that. But, you know, theoretically speaking, if the board isn't, you know, secured to the table in some way, you could do that, or the piece of metal or whatever. Well, the CNC machine isn't going to know that. It's just going to continue along its merry way like nothing ever happened. And that means you're going to get weirdnesses in your cut, in your final product, because at some point the machine will have, you know, stretched the whole design out to the right a little bit because you pulled it out to the right, but it won't stretch it to the left, which gives it a really strange kind of look to it, and you'll, you know, it would be undesirable. So for that reason, CNC machines are pretty much specifically designed to have as little human interaction as possible, to reduce the number of sort of variables that you can't account for when you're programming a CNC machine. So for us, controlling a CNC machine instead comes at the other end with CAD programs. So those computer-aided design programs I was talking about. SketchUp is a CAD program. Fusion 360 in this presentation is a CAD program. SolidWorks is a CAD program. ZBrush, Sculpt, Maya, Blender, a whole bunch of these are all CAD programs. EagleCAD, obviously it's in the name. OpenSCAD. Like these are all examples of CAD programs. But there are, it stands for computer-aided design. Or computer-assisted design, whatever you prefer. I guess technically, the technically correct one is computer-aided design, but really, I mean, it's not like it actually affects anything to say computer-assisted or computer-aided. Anyway, but there are other ways that we can affect the process as well in the intervening steps between. So creating something with a CNC machine usually requires 3 kinds of software. You've got your computer-aided or computer-assisted design program. You guys should be somewhat familiar. Again, this is how you create things in 3D on your computer or whatever. This is what we spent all that time working on a temple in SketchUp, you know, was to get you guys familiar with at least some kind of CAD program, or at least exposed to it, you know, so you could look at it and go like, okay, so this is what it does, and it's not as scary as, you know, I originally thought, that sort of thing. But that is the That is the whole idea behind those programs, is it allows you to create more complex designs. Uh, I guess more easily there are some weirdnesses when working with those programs that tends to kind of throw a wrench into the whole this is easy to use thing. There's definitely a learning curve, but it becomes a very powerful tool once you've overcome that learning curve for any particular program that you're working with. And you've got CAM programs, and CAM stands for Computer Aided Manufacturing, different from a CAD program. What this does is it turns your 3D model into a set of instructions for the CNC machine. And the reason for this is there needs to be some way to translate your 3D design into a set of steps that the CNC machine needs to follow in order to manufacture your design. And it's kind of actually remarkable in that sense, because that whole process has been automated so that computers can actually convert these 3D models into steps. A lot of times, just like 3D printing, it involves breaking it up into a number of smaller parts that have sort of sets of algorithms in order to generate shapes. So like they might have, a set of algorithms in order to make a cylinder, and a set of algorithms to make a cube, and a set of algorithms to make a cone, and stuff like that. And then they'll break the object that you created up into these shapes or parts of these shapes, and sort of incorporate these algorithms and pre-processed or pre-planned steps and stuff like that. Or it might break it up into layers and generate steps based on how it would construct each individual layer, and then sort of slap all those layers together into a 3D shape so that I can cut it out into, like a cylinder or something like that. Cut it out of a cylinder, something like that. The process might vary from CAM program to CAM program, but generally they all follow a similar sort of design process. And then they turn it into G-code, which I think I showed you guys G-code, maybe? Anyway, G-code is just, if I haven't, G-code is simply sets of coordinates. It's really all it is. It's sets of coordinates. So when these algorithms go through and determine the shapes, or they break everything up into layers and determine the path of the tool, whatever the case may be, the whole end result for them is they output a set of coordinates. So it might be like you're trying to, oh, right, new hard drive. I don't have paint on my bar. So it might be you're trying to cut like a shape that looks something like this, some sort of weird kidney bean thing out of a piece of wood. Well, the CAD or the CAM program will come through, and it will recognize the particular shape that you're trying to cut out. It will sort of find, either equations that fit, or replace it onto a graph in order to generate a set of points that it should work with. And it will feed these points into your G-code file. And so your G-code file will basically just be a set of coordinates that represents all these points. And then at that point, all the machine needs to do is simply be given a starting point, be given an ending point, and be given all the points along the way, and it just moves from point to point. And it's always going to be in a straight line, so as you have curved shapes, it will insert more points along the curve in order to generate a smooth cut that looks like a curve. But end result is the machine will basically be given step-by-step instructions to cutting something out that you designed on the computer. And that's the whole point of the CAM step, is to convert it into something that the CNC machine can work with. That's what G-code is. It's just a set of coordinates. It's called G-code because it's meant to be interpreted as a set of instructions for a machine. And on top of that, it has more than just coordinates. G-code can also contain basically specialized instructions that tell the machine to stop and wait for, a replacement on the tool, to move at certain speeds, to spin the tool at certain speeds and things like that. So it contains more commands than just coordinates. Then the G-code, or excuse me, the CAM program usually feeds, you usually feed the G-code from it into the machine controller, which you can think of these like drivers for the machine. The machine won't work otherwise. So, if you've got a CNC machine hooked up to your computer at home, your computer needs some way to communicate with it. And the irritating thing is everything talks in different languages, even though they might all be talking the same programming language, just because everything has its own set of commands, and you can't necessarily assume that something's going to have the same set of commands. Now, you've got stuff like plug and play from Windows, which was a big deal back in the early 2000s, like a big deal, like plug and play. Oh, you just plug it in and it works. And that was just because there was more of a standardization across the board. Manufacturers were creating mice and keyboards that input standardized commands to a computer, and a computer was leveraging those standards. So stuff like that means that today you can plug in a keyboard and have it work automatically. Today you can plug in a CD drive to your computer and have it work automatically. That used to not be the case back in the day. Now, the CD drive thing, a lot of that has to do with the fact that there are drivers already pre-installed for standardized CD drivers. But again, there wasn't always a standard for that kind of a thing. But I digress. Something like this is so your computer can actually communicate with the CNC machine and send it commands in order for it to do its thing. If you don't have a machine controller, you can't control a machine. And this is not literally a controller like an Xbox controller or something like that. This is a piece of code. So, piece of code. I turned Minnesota in there. I don't know why. What, Irish maybe. Anyway, it's not a physical controller. It's a bit of code. But you guys probably already knew that. So, insofar as software is concerned that you can use for a CNC machine, there's all kinds of CAD programs. You got freeform programs like Blender and 123D Sculpt, and these are very artistically based programs. So, if you're creating, I don't know, like a 3D orc for a video game, these would be fantastic options for that sort of thing, because they allow a lot of freedom. You can do all sorts of weird things with 3D models, all sorts of organic shapes and curves and things like that in order to generate more natural looking objects, and that can be kind of their specialization. However, once it's created, it can be difficult to export it to something to be printed out, because there's no set size necessarily. It's up to you to sort of figure out the proportions, things like that. But for freeform 3D modeling, this kind of stuff is fantastic. And you got easy to use with some accuracy, and that's like Tinkercad and 123D Design, 123 Design and SketchUp. You guys use SketchUp, obviously. I'm sure you guys have memories. Tinkercad, I'm sure you guys will all agree, is easier to use than SketchUp, but these are all considered sort of easy to use programs. SketchUp, you draw a shape and you pull it out and turn it into a 3D shape, and boom, done. You do the measurement thing in order to align things. You can combine shapes in order to create more complex shapes. Tinkercad is much the same way, except it's even simpler. It's just drag and drop shapes, and you can make some shapes like negative shapes, so you can cut holes out of things, stuff like that. 1-2-3 design, we tried to get running that one time, and it didn't. So that could be something that's removed from this. And then we've got professional class. So we've got Autodesk Fusion, Fusion 360, is actually included among the professional class bits of software. And then you've got SolidWorks and Libre. These are all, you know, if you go into an engineering field, you'll probably become, I don't know why I wanted to add an extra B in there each time, probably become familiar with one of these programs or some professional level CAD software. And these are considered professional because they're very rigid, they're very strict. You have to abide by very specific rules when you're building something. And what do I mean by that? Well, okay, so like, you know, in this example, Fusion 360, you're building something with Fusion 360. You draw a shape. You have to dimension that shape. You have to give it very specific dimensions in feet and inches or meters and, you know, centimeters or whatever, before you can do anything with it. It's not considered a real shape until you do that. And then you have to, you know, you can take that two-dimensional shape and turn it into a three-dimensional shape, but then you have to dimension that as well. And you have to dimension basically everything. And all I mean by dimension is you have to tell the computer how big it is. So you literally use a built-in measuring tool in the software. You select a line on a shape and you tell the computer, okay, this line is supposed to be 15 inches. And it goes, okay, it's supposed to be 15 inches. And then you take another line on the shape and you go, okay, this line's supposed to be 9 inches. And it goes, okay, it's supposed to be 9 inches. And then, you know, it'll automatically resize everything because everything's got to make sense. And it'll tell you if, like, it doesn't make sense physically speaking, or if you have too many measurements on it or not enough measurements on it, things like that. It's very, very specific and very, very finicky. But the end result is something you can be assured of its dimensions. You can be assured of how everything's supposed to fit together. It is meant for engineering purposes because these things are meant to provide, you know, the smallest fault tolerances possible, basically the smallest margin of error. And they're meant for these sorts of things. So it's not going to be as easy to create organic shapes and stuff like that as it is in a freeform program. Like imagine you're drawing that orc I was talking about in you know, Blender or something like that, and you want to give it like, you know, bags under its eyes and like weird orc wrinkles and jowls on its face and stuff like that. with with something like Fusion or SolidWorks, you would have to dimension those. Say like, okay, so the arc, the radius of the arc that makes up the inside of the bag of his eye is going to be, you know, 90 degrees, and then there's going to be a, you know, a straight line that goes from the bag straight up to the, you know, the bottom of the eye, and that's going to be, you know, a quarter of an inch long, and then the eyeball is going to have a radius of this, but only this much is going to be visible, and it would be just insane. It would be a lot of work to do, way too difficult. So for that reason, professional is more for stuff that you would build, and freeform is more for organic things and more for artistic sort of purposes and stuff like that. Professional is engineering, freeform is artistic, and then easy to use is sort of in between, you know, sort of. So now we've got the CAM side. Computer-aided manufacturing. Well, there's a whole bunch of different brands. Here's just a few different examples. MeshCam is a way of converting CAD designs into G-code for use on a CNC machine. Works across a bunch of platforms. VCarve, great for ShopBot. OtherPlan, great for OtherMill. It's just OtherPlan, singular. I don't know why there was an S there. Anyway. Whatever, you know, that comes down to the type of CNC machine you have and what you're comfortable with and whatever. That's less sort of wide open than CAD. CAD has a whole bunch of options, and a lot of those are dependent upon what in particular you're trying to go for. CAM as well, but it's more about what you're using and what you're familiar with. And ShopBot and Other Mill are just particular brands of CNC machines. Then you got the machine controller. You can get custom machine specific programs. So again, the ShopBot program for ShopBots, OtherPlan for Other Mill. So OtherPlan is a CAM program as well as a machine controller. So there you go. Then you got OS specific ones like Mach 3, not attributed to a specific brand of CNC machine. However, it will work specifically with Windows. So there you go. Linux CNC for Linux. Duh. Now, this seems like a fair amount of stuff, but most software at least has a couple of these steps integrated directly into it. So, for example, most CAD software will export directly to G-code, skipping the CAM step. Likewise, as you can see here, OtherPlan is CAM as well as machine controller. So, you can make something in SolidWorks and export it to OtherPlan and turn it into G-code and then use OtherPlan in order to control your other mill, or you can just, you could even, whatever, you could create the G-code in SolidWorks and send it to OtherPlan and get it cut out. I know, terribly exciting stuff. But a lot of times, everybody's trying to sort of simplify things and combine combine as many steps as possible into one to make it easier for users and faster and stuff like that. So this was meant to follow or meant to precede the beginning steps of Fusion 360, but we'll spend a little bit more time talking about this kind of stuff. So now there are parts on a CNC machine. Sorry, I had to cough there. There are parts on a CNC machine that, understanding the terminology is probably good. So a cutter, so in this case, when we're referring to a cutter, we're generally referring to a mill type CNC machine or a cutter type. It's sort of odd. The mills and cutters are very similar. But in this case, I guess it would be more of a cutter, especially because we're using cutters. So the cutter is the actual bit. Think of the drill bit on a drill, the actual Phillips head part of a screwdriver, things like that. This is the actual bit that does that interacts with the medium and does the cutting, hence cutter. Cutters come in a variety of different shapes, basically, in order to fulfill a number of different jobs. You've got flat end mills, which are really great for just like ripping material out. Ball end mills, which are good for, actually getting into, harder material because there's an easier sort of grade into it. There are actually a whole bunch beyond just flat and ball end mills. But anyway, these are just a couple of examples. You've got, when you're referring to cutters, you've got the shape as well as the flute length. And the flute length is basically the length of the spiral on the thing. So these are actually different styles of flutes. As you can see, they can be in the spiral can go in different directions, which affects how it's going to cut things. Think about, a propeller on a plane or a fan or something like that. It's meant to spin in a very specific direction. If it spins in the other direction, the air goes the other way. It's a similar idea with material, obviously not a one-to-one comparison, but it's very similar. So an upcut spiral is going to be very good at, removing material very quickly. In broad strokes, a downcut spiral is going to be very good for more precise and smooth kind of cuts. So it's good for coming through and cleaning something up. A straight flute is very, very rough. As you can see here, there's almost no spiral to it at all. There's just very little bit, but you know, it's good for just cutting out big chunks of stuff and working with very soft material. Taper end mills, as you can see, if we go back, I thought that was the link for some reason, good lord. If we go back, you can see that these generally are at the same thickness as the rest of the tool. However, a taper end mill, there might be a little bit of flaring out, but they come to a point at the end very abruptly. And these are good for, you know, again, getting into harder material and getting it started for, for larger cutters and things like that. And then there's the number of flutes. So again, the flute length has to do with basically the distance from the spiral to the next part of the spiral. So that can be considered flute length, right? So over here we can see it as from here to here. Boop. Flute is simply a fancy term for this particular the part that sticks out on the spiral itself. So as you can see, this has two flutes. It's got two prominent ends that stick out. The flute length is, you know, how long the flute is. Then there's the tool diameter, which is how thick the tool is. You got the cutter diameter, which is how thick the cutter is. So the tool diameter can be different from the cutter diameter. For example, the ball end mill here would have a different tool diameter than it would tool diameter than it would a cutter diameter. Not as dramatic as a taper end mill. A taper end mill has a much different tool diameter from, much different cutter diameter from a tool diameter. But there is still a difference. Of course, the overall length is how long the tool itself is. All pretty straightforward stuff. Then we've got terms as far as the actual cutting with CNC machines is concerned. So the speed of the CNC machine refers to the rotational speed of the cutter in revolutions per minute. And these tend to be very, very high. You know, we're talking about 500 revolutions per minute, 600 revolutions per minute. So what is that, 10 times a second? Pretty fast. Then again, they could be, you know, much slower, maybe only 2 times a second. Though I don't recommend that. You generally want to be spinning quite fast. It depends on the material. Then you got the feed rate, which is the speed that the cutter is moving through the stock. So if we've got our tool here, let's give it a couple of terrible flutes on it. So whereas the speed is the rate at which it is rotating, the feed rate is the rate at which the tool is moving through the material. There you go. Pretty proud of that. Excellent. Anyway, so you've got speed and you've got feed rate. Mouse drawing. All right. Then you've got, oh, well, there used to be more there. Anyway, the reason why it might matter is it's good for the life of the tool as well as the end result. So if you move too quickly, if your feed rate is too high and your speed is too low, you risk breaking a cutter. because you're basically putting too much stress on the cutter to get through this hard material, or the material that's too hard for the speed you're going, and the tool ends up breaking. Um, Loss of accuracy, again, if your tool, your feed rate is moving, it's moving too quickly and it's not spinning fast enough. It could be not removing the right amount of material, or it could be not removing all of the material before it moves on from a particular area. So you might have like little bits here and there that still are just kind of existing out there. In addition, the faster a machine has to move in order to, um, in order to make a cut, like if you tell it to move faster, you do introduce some inaccuracies into it. On top of that, you move fast enough, you run the risk of actually moving the material it's working with, which would definitely lower accuracy. Wasting time. So if you have it moving too slowly and it's just sitting there and it's spinning super fast, and it's already cutting all the material away and it's just kind of hanging out in an area for longer before it moves on, well, it could certainly be moving faster, if you're cutting faster than you're moving through the material. And poor finish. Well, again, you're spinning too fast. You could actually just rip extra chunks off. It could be very rough looking, that kind of thing. So what is the correct speed and feed rate? Well, not that you guys are really going to have to deal with this, at least at first. Generally, you just go with the recommended settings. A lot of times, because they sit there, the people who make these things, they sit there and they try and figure it out. They're like, okay, so what if we tried it at this particular feed rate and this particular speed with this particular material and doing this particular thing? So with this particular tool. So generally, they have a pretty good idea of what the speed and feed rate should be for most situations. Now, obviously, you would tweak it. Why are there random typos? You would tweak it to your tastes as you would work with this. So, it's not always going to be the same thing. It's not as easy as just simply, plug and play to bring things back to where we were before necessarily. But, for the most part, the recommended settings, they do a pretty good job of figuring out what it should be. And then materials that a CNC machine can work with. Well, a lot of stuff. You've got MDF, medium density fiberboard. So, think of kind of like plywood, except, let's see here. It's sort of like cardboard too. It's very hard. It's very strange to describe. You ever worked like, done arts and crafts or something like that in elementary school, and they brought out these big sort of brown boards that are light and floppy, but they're not paper, but they've got sort of like a soft textured back to them, and the front of them is kind of glossy and slippery. This is a very strange thing to describe, but anyway, that would be something like fiberboard. That would be an example of it. That would be, I'm not sure what density it is, but that would be an example of fiberboard. Plastics, no surprise there. Look at all them plastics over there on the right-hand side. Wax, there is machinable wax, so you can actually take a tube of wax or something like that and hook it, like put it in a CNC machine and have the CNC machine cut a candle out for you or something. Who knows? Some sort of weird shaped candle. That would definitely be something that's possible. Foam is definitely a thing. You've got very varying hardnesses of foam. Well, the harder foams you could certainly machine with the CNC machine. Polyurethane tool boards, which are also a version of plastics, but they're much denser. And metals. Corrugated plastic. Corrugated plastic like I can't find the word right now. Anyway, it can be possible. The thing is that machinable materials doesn't necessarily just refer to its strength. It refers to its brittleness or lack thereof as well. And you want something that that's not terribly brittle, because the thing is, working with a CNC machine, tends to create a lot of vibration throughout the material and a lot of stress on the joint stuff. So if material is strong enough and brittle enough, as you're trying to machine through it, rather than cutting the material, you might just end up breaking off extra parts of the material. So for that reason, I feel like corrugated plastic is more brittle. Yeah, so it might not, I don't know, who knows. It might be, it might not be enough. But yeah, so a whole bunch of different materials though. And obviously wood, duh, you can work with wood. Um, so there's, you know, there's that. You can rest easy knowing that it works with wood. But yeah, so that actually does it for the CNC presentation. At this point, it would just be all about using Fusion 360 to make a bookshelf. And as you can see, there's a lot going on. But yeah, so we'll just go ahead and have that be it for today. Next week, we are going to get started on an entirely different subject from CNC machines and 3D printers and all that good stuff. So we'll spend some time, spend a few lessons with this new material next week, and hopefully you guys find it interesting. And then we'll just go somewhere from there. But let's go ahead and do the poll questions, and we'll do question and answer time. As always, if you don't have any questions after the poll questions are over and done with, you're more than welcome to head out. You know, have a wonderful weekend, and be ready for an entirely new subject on Monday. Otherwise, I'll be here. You can ask me questions. We'll do the thing. You could be related to the class, you can not be related to the class, whatever. But yeah, you guys know the drill.